Hello. In this video, I'd like to talk about lenses and try to demystify what they are and how you'd use them. Hopefully this will be helpful to people who are just starting to try to use lenses, or maybe have just begun and want a little bit more information. So let's take a look at the core idea of lenses, in that we have a getter and setter combination that we can use to traverse nested structures. Let's first start by trying to define our nested structure. We will say data foo is equal to foo, and we'll give it a couple fields. I'll add a bar field, which will be an int, and to make this actually a data type and not just a new type, let's add a baz field that is a char, and we'll derive show. Now let's create a couple functions that give us our foo and our internal tuple type. So I'll say my foo is a foo, and my foo we'll call my tuple, and the char a. My tuple will be an int, and we will set this equal to 1, 1, like so. So now we'll think about how can we possibly write getters and setters for our foo data structure. And these won't be that hard to write. If we write get bar, it'll take a foo and give us an int, and get bar is simply just bar, like so. If we want to call set bar, we would take a foo, a new int, and get back an updated foo. So set bar might look something like this if we use record syntax, and we can see that that compiles as well. So now let's consider if we were trying to write a setter and getter for the second element of our tuple. So we'll write a get _2, and this will take an AB and give us back a B. And this is just equal to second, like so. And if we try to do a set _2, well, that'll take an AB, a new B, and give us back an AB, like so. When we write our definition, we can ignore the old B, take in the new B, and return our AB, like so. So here we've written very simple getters and setters for our data types. Now, could we combine these into a single structure that we can call a lens? Let's take a very naive approach of defining data.lens as being a data constructor that takes in two things. It'll take our getter, and if we look at the pattern between our getters, we take in some structure and we focus in on some field in that structure. So we'll say that this is a function from the structure S to our field A. And the second function is the setter, which needs to take in the structure, an updated value, and give us back an updated structure, like so. Now we'll need to parameterize this data type by these two values. And now in order to use this new data type, let's construct our bar lens, which will be a lens of our structure is foo, and our internal value is int. Bar L will be a lens of get bar, set bar. And we can do the same thing for our second field of our tuple. We'll make an _2 lens. That'll look at a lens of AB and focus in on the B. Well, this will just be lens of get _2 and set _2, like so. So these hook up our two getters and setters into a single lens type. We don't really need these getters and setters anymore, so let's actually just rewrite our lens to do those two things. And we can delete these. Same thing for this _2 lens. We can just call second here, which gets rid of this, and we can write a lambda expression, which does exactly what our function did before, like so. Now that we've written these lenses, let's try using them. In this situation, let's update our main function to try and print the second field of our tuple. So we'll use our _2 lens with my tuple, and now we need some way to get the getter function. Well, let's just use record syntax in order to access that. We'll go up to our lens definition and say view will be our getter function, and set will be our setter function, and this compiles. So let's see if this works. If we do stack run, we'll see that it accesses the second field. Let's go ahead and try updating the second field to some other value to make sure it's actually getting the right field. And everything seems to be working correctly. Well, can we also try setting the value inside the tuple? Let's print. We'll call set with our lens. We'll need to pass in our structure, my tuple, and the new value that we want to change it to. If we run this, let's see if that works. And here we can see that we have an updated tuple with 1 and 10. Fantastic. Now, we run into our first issue here. What if we want to update the second field of bar inside of foo? Well, we would want to pass my foo here, and we'd want some way to compose the bar L and the _2 lenses. Unfortunately, they do not compose well. The reason for this is we are using a data type for our lens, and we would have to define some way of composing them. Furthermore, we won't be able to use function composition via dot. Well, I'd like to use function composition, so how could we go about using that? Well, we'll have to think about lens a little bit differently. How can we turn lens into a function? If we squint and try and think about this, one thing that we could consider a lens being is something that actually allows us to take a function that updates an internal type and promoting it to a function on our structure. So if we have a function that updates a field of A, then we can promote that to a function that updates a structure that contains such a field. Well, if we have this type that's a function, can we create one via our getter and setter functions? Let's write a nice helper that's going to take in our getter and our setter and gives us a lens. And I'm going to name these parameters based on what they take in and what they produce. So we have SA and SAS, but we have two other implicit parameters, and those come from lens. We'll notice that lens is a type alias, so we actually have an AA here and an S. Now, we're going to play a little bit of type Tetris. Using our getter and setter functions, we want to produce something that will update our structure. So the first thing we need to do to update our structure is to use our AA to update an A. But we don't have an A, we only have an S. How do we get an A from our S? Well, conveniently, we've passed in such a function. So if we use SA on S, we now have our A. We can use AA to update it. And finally, we need to update our structure. How do we go updating our structure with this A? Well, we have a function that takes in our structure and an A and produces an updated structure. So we just have to pass in the structure as the first argument and our updated A as the second, and we've created our lens. Let's update the rest of our types to now use this helper function. And now we need to write functions for view and set. So let's consider what view is. View is going to take in our lens. It'll take in our structure and some value A that we want to project on, and give us a function that takes in the structure and produces our value. Simple enough. We will set this as undefined for now. And for set, we run into a similar situation where here we're going to want a lens that looks at our structure and a new value and produces an updated structure. And let's swap the order of these because I like having the value come first. So for set, we'll also set that equal to undefined. And as I said, we swap these. I like having the value come before the structure. And everything compiles. So now we need to decide on implementations for set and view. Well, let's start with set. For set, what we need to consider is that we have a lens, we have an updated A, and we have a structure. And we simply want to override the existing A inside of our structure. So we're taking a function that's an A to A, as well as our structure, and this should give us an updated structure. Well, how do we override an a with our new a? Well, one such function that does exactly this would be to say const a. And you can see that this compiles. Let's check to see if it works. By commenting out our view code, we can now do stack run. And sure enough, we were able to update the second field of our foo structure. Perfect. We now have composable lenses. But how are we going to write view? This is going to present a problem for us. Let's follow the same pattern. We have our lens L and our structure. And what are we doing with the A? Well, we're just viewing it, so it remains unchanged. Do we have a function that exists that takes in an A and produces an A unchanged? We do. It's ID. But if we save, we can see that we're not matching our types correctly. Here, we're expecting a type A, but getting back an S. And that makes sense because we promoted our A to A, ID, to a function of S to S. Well, how would we get out our A value from our structure? And the answer is we can't. Not with our lens written as is. So what can we do? In this case, let's consider thinking about how we might take a structure S and get out some additional context. Now, when I think of structures and context, one of the first things that comes to mind is functors. So can we say that we take an A and return some functor A or some context of A and promote that to a function that takes in our structure and produces a functor of that structure or some context related to that structure? Well, if we do this, we'll need to actually bring f into scope. And the thing is, we don't know what our f is going to be. I'd like to keep my lens parameterized by s and a and let f be decided later. And you'll see why this is relevant when we actually write our implementations. So in order to delay evaluating what f is, we need to use existential quantification. So we're saying for any functor of f, if we have a function from a to fa, we can get back a function from s to fs. Now this will require the language extension, rank n types. So let's go ahead and add that. And we'll need to update the rest of our types in our application. So the first thing to consider is that we no longer here have an AA. As you can see in our lens type, it's an A to FA. So let's update that name. And because this is no longer producing an A, we can't use our setter function. But what we can do is fmap on it, and that'll give us our fs. So we just simply change this to fmap because we have an fa, and we can fmap on this function to get our fs. Now we'll need to make a couple changes. Let's leave view as undefined, and let's work on set, because we know that set already worked before we switched to the functor context. So how would we get set to work? Well, we need not an A, but we need an FA, and that'll give us an FS. Now when we set, we need the structure, and that's all we really need. We don't care about our A value, we need no additional context. So what sort of functor can we provide that doesn't have an additional context? Well, if we think about that, it's the identity functor. So let's add the identity functor here. If we say new type identity A, we can say that this is identity run identity fa, and we can turn that into a functor by writing the functor instance for identity, where fmap f on identity A is equal to identity fa, like so. So here we have a context, a functor context that we can use that will allow us to retrieve a value back out of it. So instead of const A, we can say const identity A. And if we save that, we can see that now our function is producing an identity S. And our error over here basically says that S is not the same as identity S. So we just need to call run identity on our identity S to pull out our S value. Fantastic, it compiles. But what can we do about view? Now remember, we couldn't use view before we added the context. So let's try and implement it from scratch again. So here, what do we provide here that takes an A, produces a context A. Now keep in mind, whatever context of A we produce here, we want that context to remain in the fs. And we don't care about the s anymore. Our view isn't returning an s, it's returning an A, so we can discard the s. Now, is there a way that we can provide context that retains the A, but doesn't care about whatever its right-hand side is? It doesn't care about the s. Well, that sort of reminds me of const, and there is actually a const functor. So let's go ahead and implement the const functor. We'll have some const be A, and A will be a phantom parameter where we don't care about the A on the right-hand side. This means that we can freely change the A, but still retain whatever we initialize const with. And we can write a functor instance for this. Here, while we're taking in a function f, which should be a map from A to some other value, we don't have an A to perform that function on. So we can ignore this. And all we need to do here is construct a new const b. Because the A is a phantom parameter, the type system will decide what the A is when we construct it, and it allows us to change from one const type to another using functor. So in this situation, we can now just take in our A with const, and we can see that this works. For the most part, we get the same error as before, that A is not the same as a const AS. So you can see that we went from a const AA to a const AS, and in order to get our A out, we simply have to call run const. And everything compiles. But does it work? Let's find out. We now want to take our view and compose. So if we view varl_2 of my foo, we would expect this to be able to correctly traverse and print out the value of 2 from our tuple. If we run this, we see that it does indeed work. Fantastic. Now that we have view and set, it might be nice to write an additional helper function, which allows us to modify some value inside of our structure by providing a function for modification. So we'll say we have a lens SA, and given a function that updates an A, we can get a function that updates the structure. So if we want to use this, we have our lens, we have our F, and we have our structure. What would we do here? Well, similarly, we have our L, and now we want a function that updates our A and returns a context of A. So if we were to write this out, we might consider calling FA. And let's keep in mind that we want the structure again. So this is very similar to set. We'll want to use identity. So if we use identity on our structure, then call run identity on the outside, we have a version of over that will work. And we can simplify this using eta reduction to say that this is identity.f. Let's take a look to see if that works. So if we call over, and we say +10, we should now see an updated version of my foo, where the second field of our tuple has been incremented by 10. And sure enough, that works. We'll wrap up this video by trying to make our lenses a little bit more powerful. Consider the situation where we want to call set on the second field of our tuple, but change types. We'll find that this will not work. Because our lenses are defined as going from A to A, we can't go from an int to a char. So let's make them a little bit more abstract. Instead of going from A to FA, we'll go from A to FB. Now keep in mind, by changing types internally, we've also changed what structure we're talking about. We no longer have an int, but we have an int char, and so we'll need a new structure type, which we'll call t. So let's parameterize this by those additional types, and we'll need to go through and update the rest of our code to use this new lens type. So here, we'll consider that our setter, it no longer requires that the type be A. We can now set it to a different type, B, and we'll get a new structure back called t. So if we parameterize this, we'll realize that we need to rename this function from SAS to SBT, and nothing else has to change here. For foo, we're not going to change our structure. Our bar lens will keep it as the foo structure, and we're not going to change types. For _2 lens, though, we want to be able to allow this to change. So it'll go from a tuple of AB to a tuple of AC, and we'll parameterize A and B as B and C here. And nothing else needs to change there. Our view function, we simply need to add the extra parameters, but because we're not changing the A, nothing else needs to change. For the set, we'll consider that we're now passing in a B value, so we must be in the new structure T. And finally, we'll update our over to go from A to B, and again, we'll have potentially a new structure type, so we must use the T structure here. And everything compiles. We now have a more powerful version of Lens with very few changes. Let's see if this works. So if we start a terminal and go stack run, we'll see if we were able to update our tuple, which we were. We can now see that this tuple went from an int to int char. And if we don't like the repetition for cases like this, where we're not changing our structure or our internal type, we can create a simple type alias. Which provides that duplication in the type for us. And now we can clean this up and use our lens prime. And this ends what we want to talk about via lenses. Hopefully this gives you an idea that lenses aren't something super mystical, that don't require a lot of demystification. You can simply think of them as these functions, the getters and setters, and a way of combining them that gives us access to both. If you found this helpful, feel free to let me know, and hope you enjoyed it. Take care.